Today's class will discuss about slip power recovery schemes. Okay, so I hope so. So we will recover the slip power of the induction motor. I hope you remember in case of the induction motor what is the slip power. What is slip power in the induction motor? Slip power in the sense it is uh, it is the power. I can say like this that see the air gap power is there. So in the induction motor, you take this as the stator, okay, leave the rotor here. Okay, so this is the rotor. So the red color one is the rotor. Okay, this is the rotor. This is the stator. So you give the supply here to the stator. Then there is power. So anyhow, it is everything is a power flow. So this some air gap power is there. We call that as PAG. PAG is the air gap power. So this power will enter into the rotor. So now this power, so after it enters into the rotor, a part of the power will do the work on the load, mechanical load. There is a mechanical load is there. So a part of the power, which power? Air gap power. A part of the air gap power will do the work on the load, on the mechanical load. So other than this power, the remaining power, the power which enters into the air gap, that's called air gap power. So this power will enter into the rotor. So out of this total power, a part of it will work on the load, or you can say a part of it will go to the mechanical load. So the remaining power you can call it as slip power. The remaining power you can call it as slip power. And the formula for that also we have got in case of your induction motor, that is S into PAG. Okay. So what is PAG? PAG is the air gap power, or the power enters into the rotor, or input power to the rotor. We can say different names we can say here. So the slip power is nothing but S into PAG. Okay. So this we already got in the previous classes itself, or you revise yourself, then you will get this answer. Now here what we are studying is that how do we recover this power? How do we recover this slip power? Okay, what are the ways? So why do you want to recover that? So that we can use that in somewhere else. So that is the purpose of using this power. Okay. So now what are the different schemes are which are there for this recovery of the slip power, that we will study from now onwards. So mainly there are two schemes are there. One is Sherbius system. The second one is Kramer system. Now we will study both of these today, if possible any one, or if time permits both. So first we will take Sherbius system. So I told you already that both the systems are, what is the purpose of both the systems? To recover the slip power. So now we'll see here. First we'll study the conventional system. That is conventional Sherbius system we can say. So in the Sherbius system, the first one is conventional system. So we'll just draw the block diagram of this first. So these are the three-phase supply. This is three-phase supply. So then stator is there. Some stator I will write here. Assume that it is connected in delta. So how do you connect? You connect here. Okay. This is stator. Then it is coupled with the rotor. Assume the rotor is star connected. Any case you can take, there is no problem. Then the rotor circuit we are discussing now. Of course, this rotor is coupled mechanically to one load. That load I am not going to draw here. Please see here. Only we are interested here. Please answer. Is it audible?
Yes, sir.
Okay. The rotor power. Now we are discussing about the recovery of the slip power. Yes. So we will not worry about whether we connect the load or not. Mechanical load part I'm not going to draw. I will draw only the rotor side part. That is electrical circuit I will draw. So this rotor is connected to one converter. That converter you call it as rotary converter. Okay. So now you look at this circuit diagram. I will just tell you the flow here. I told you we are recovering the slip power. So the slip power you will find out, okay, with the rotor terminals. So you are giving supply to the stator. So the induction motor is working. Now it is driving some load. Okay, we don't need to worry about that load. Then we will discuss about the slip power. S into PAG. So this power is through the rotor, and that so this rotor power, that is slip power, you will give to a rotary converter. Rotary converter in the sense which converts something like this. That one example we have seen last class. This uh, in the static rotor resistance control, what we did in the static rotor resistance control, if you recall, that the rotor terminals of the rotor is connected to a rectifier. Just recall that you connected to a rectifier, so that AC will be converted into DC. The same thing, this rotary converter, in the sense this is a system which converts this here the rotor power, AC power, into DC. You see here there is a DC is there here. So you can consider this as a rectifier also if you want. Just it's a in generalized it is a converter which converts this rotor power into DC. Okay, anything you can take, whether it is rectifier or control rectifier, uncontrolled rectifier, anything you can take. Now this power, where this power is going now, this power is going to DC motor, because this is a DC now. So this AC power which is at the rotor side is converted into DC using this system. Then that DC power goes to the DC motor. So when once the DC motor takes a DC power, what it does, it converts this electrical energy into mechanical energy. So that mechanical energy is going to a induction generator. And what the induction generator does, it takes mechanical energy and it will convert to electrical energy. So here the electrical energy which is there, which is in the form of DC, it goes to the DC motor, then it generates mechanical energy. It generates mechanical energy. Then this mechanical energy goes to the induction generator. Then this induction generator will generate electrical energy. Now this electrical energy is coupled to the bus bars once again. Same bus bars. Okay, so from the bus bar to the stator, then stator to the rotor is coupled, then rotor to the rotary converter, then that electrical energy goes to the DC motor. Now it is a DC, so DC motor will convert this electrical energy into mechanical energy. Once again, this mechanical energy is converted into electrical energy using the induction generator. That generated electrical energy is pumped to the bus bar. So indirectly we can say the slip power which is there here in the rotor is going back to the bus bar. So you can call this as a recovery of the slip power. So this is a conventional system. This is conventional system. Okay. Now we will draw the static Scherbius drive. Draw the static Scherbius drive. Okay, what is the static share-based drive? Is that simple thing? Static devices we will use. That is power semiconductor devices we will use to recover the power. Nothing else is there here. Okay, so same thing. Okay, so this is the bus bar. Then you have stator, rotor is there. So the stator. Now you have the rotor. Okay, then we'll do one thing. You connect the supply to the stator. Then what do you have here? The rotor is there. So it is coupled mechanically to any load. Okay. Okay, and then now the rotor, we don't need to worry about this part. Now we need to worry about the rotor side connection. Okay, so rotor side connection, where it goes is that I will just rectifier. Then you have another bridge is there this side, but this is a controlled bridge. Now please answer: is the screen visible?
No, sir. Less, sir.
Yes or no?
No, sir.
Is the circuit diagram visible now?
Screen visible or less, sir?
Okay, okay. Just I will.
It's visible till a minute back.
Okay. Now please answer: is it visible now? I will just show you now.
Visible, sir.
Okay. Okay. So we'll do this remaining connection here. Okay, this is the circuit diagram you will find out here. Okay, so here you have two bridges. Here you have two bridges, and this is the circuit diagram for the static or block diagram for the static share based drive. Okay, So now, please see this now. Now see how it works now. Just see this. The flow is very same. That the flow which I have shown here, the flow which I have shown, okay, in case of the conventional Scherbius drive, the same way here, except the difference is that you are using entirely here power electronic devices. You are not using any kind of machines here. Entire thing is power electronic device. Main conversion is happening through the power electronic device. I will show you here. See this once again, same thing. So you give the power to the stator. This is the stator. Then the rotor does some work. Other than that, you call it as S into PAG, that is area, that is slip power. So this slip power you tap here and you send it to this three-phase bridge rectifier. Then what this three-phase bridge rectifier does, it converts this AC to DC. Then that DC is connected to, now what is this once again? You can call this as inverter right now. Whereas you can call this as rectifier, because this rectifier converts AC to DC, whereas this inverter, now you got the DC here, the DC you are sending through an inductor LD, so this LD will maintain the current ID almost constant. It maintains the current almost constant. So then the DC current and DC supply you are giving here, okay, DC supply you are giving here, then the DC you are converting into AC once again. So here what exactly you are doing is, now you are recovering the slip power here and you are sending to the rectifier. Rectifier converts AC to DC. Then this DC, after passing through this inductor, then this DC passes through this inverter bridge. Then this is converting DC to AC once again. So this AC will connect to the bus bar through a transformer. Okay. So all the devices here, what is the purpose of rectifier here? You convert the slip power, that is AC, into the DC. Then what is the purpose of the inductor here? It will maintain the current constant. Then what is the purpose of inverter here? It converts this DC to AC. Then this AC will be connected to the bus bar through the transformer. Now what is the purpose of the transformer here is that the voltage level here, now whenever you are connecting any power supply, or whenever, see, you generate some power, you want to connect that power to the bus bar. How do you connect to the bus bar generally? So I think you know this condition, that whenever you connect to the bus bar, two important conditions are there. One is the voltage level should be same in the sense the generated voltage should be same as the bus bar voltage. Okay. And second condition is that the phase sequence should be same. These are the two conditions you should satisfy. So the transformer which we put here, so it will change the voltage. For example, the voltage here is not same as the voltage of the bus bar. Then it will change the voltage. Either it step up the voltage or it step down the voltage. Okay. Generally, it step up the voltage. Remember now, it step up the voltage. So here less voltage is there. Here more voltage is there. Generally here you have less voltage. Why you have less voltage here is that because this is rotor voltage. Rotor voltage, if you recall, in the induction motor, it is S into ER. Please recall that. S into ER. And generally you know the value of S. S is generally small value. S is generally a small value. Okay, so if it is a small value, then the EMF is also small. So if the EMF is small, then this EMF is also, the voltage you will get at the end of the inverter is also less. Then definitely you have to step up that voltage. See, here you have high voltage, you know very well, because you are giving directly the supply voltage to the stator. What about the rotor voltage? Rotor voltage is less. Why the rotor voltage is less? Because rotor voltage is proportional to the, yes, it is proportional to the slip here. Yes, is the slip here. So as the rotor voltage is less here, because of the presence of the slip here, so this lesser voltage you rectify, then you do the inversion, then also you will get lesser voltage only. You are not giving any kind of boosting here. So that boosting should be done using the transformer. Then only you will get the high voltage here. So that high voltage will match with the bus bar voltage. Then it will be connected directly. So you need a transformer to step up this voltage. Okay. I hope you understand why you want to step up the voltage, because the rotor voltage is lesser. Okay. This is the power flow. This is how the power is flowing, and this is how you recover the power. Okay. Now using this explanation, we will write some equations. Necessary equations we'll write here. First, what is VD1? We want to write what is VD1. Okay. What is VD1 here? Now it is a diode. Now it is a diode bridge. So it is a three-phase diode bridge. So three-phase diode bridge. What is the output of a What is the formula for the output of a three-phase rectifier? Simple formula that we have got already in the previous classes. That formula we will write directly here. So I will write here as 3. Okay, so better I will write this side. Okay. So now assume that the voltage here, the rotor voltage here, assume that I said it is S into ER, S into ER. Okay. So it is S into ER is the voltage here. S into ER is the voltage here. So I will write that voltage here. Okay. So how can I write this? 3 root 2 by pi into the input voltage, the line voltage to the rectifier. This is the formula I will write here. When you have let 3 root 2 by pi, this you might have studied. This you might have studied. But remember, this VL is the rotor voltage. So I will write here VLR. Okay, a rotor line voltage. It's not stator line voltage. So you should not get confused here. Why? Because the rotor line voltage, stator line voltage, both are not same. This you know very well. So this is VLR is the rotor line voltage. So I will write the rotor line voltage as something like this. Rotor line voltage I can write like this. Okay, 3 root 2 by pi into S into VR. What is VR? VR is the rotor line voltage at standstill. I will write here VR is the rotor line voltage at standstill. Combinedly it becomes VLR. So VLR is equal to here S into VR. This you must understand. Okay. Then I want to rewrite this equation further. VD1 I got the answer how much? 3 root 2 by pi SVR. Okay, VR is the rotor line voltage at standstill. Otherwise, you can replace this SVR with VLR also. VLR, what is the VLR? It is a rotor line voltage. Okay, any rotor line voltage VLR. But at standstill, you want to convert then S into VR. Okay, so S is the slip here. Okay, and then I can rewrite this equation further. How to rewrite this equation further is that see here. Here the at standstill voltage is VR. I will take VL is the line voltage here. I will take VL is the line voltage here. VL is the line voltage of the stator, whereas VR is the line voltage of the rotor at standstill. Now, okay, so this ratio is already mentioned in the data sheet of every induction motor. Generally, you will find out that I will represent it as A. So this is the turns ratio between something like this. Here you see the previous picture. Yeah, this one, stator, rotor. So there is a turns ratio is there here. So the turns ratio I'm taking it as A. What is A here? A is the ratio of VL by VR. We will remember like this. So what is VL? VL is the stator line voltage. What is VR? VR is the rotor line voltage at standstill. So this ratio, definitely every induction motor data sheet, this ratio will be given. There is no doubt in that. So now we will do one thing. From this equation, we can do something here. What is VR from this equation? It becomes VL by A. So I will better substitute this here directly, so that I may need, I may or I may need here. So yes, VL by A. This is pi. What is A? A is the turns ratio between stator to rotor. That is VL by VR. Okay. So this we got. Then what is V1 now? I want to find out what is V1. What is V1? So if you recall, what is V1? In power electronics, we have studied this thing, that full converter. This circuit is nothing but full converter. No doubt in this. Why it is full converter? Because you see here, this is AC, this is DC. So you are converting AC to DC. Okay, you are converting AC to DC. If you see this side, from this side, if you see, you are converting AC to DC. Just take an assumption. So in that full converter, we have studied this also, that this full converter can be used as line commutated inverter. Just recall this word, line commutated inverter. So a full converter can be used as line commutated inverter. See this inverter output, you are connected to the lines. So a line commutated inverter is nothing but it's a full converter for alpha, what is alpha? Alpha is the firing angle greater than 90 degrees. This we have already studied. That a full converter, when you increase the value of firing angle greater than 90, you can use that full converter as line commutated inverter. So this entire thing, this entire thing can be used as a full converter for firing angle alpha greater than 90. So the inverter here, because you see the bridge also, you see, it's a, what is this bridge? It's a thyristor bridge. So this thyristor bridge, what is this thyristor bridge? If you see from this side, it looks like a full converter. Okay, it looks like a full converter. It looks like a full converter. So now please see, sorry for the disturbance. Okay. So you see now here we are discussing about V1 value here. So what I am saying is that this thyristor bridge is nothing but a full converter, and it will work as line commutated inverter if you make the firing angle of, or if you give the firing angle for this bridges, for these thyristors of the bridge greater than 90 degrees. So this we have already studied. This we have already studied that full converter for firing angle alpha greater than 90, the full converter can work as line commutated inverter. So this we have studied. So if you recall that thing, then we will get one important observation, that what is that value here is that, so assume that the voltage here, the voltage from the AC side, I will give some voltage here. Any value you will get. Line voltage here, I will take it as Vx. Just assumption, take an assumption that the line voltage here is Vx. So if the line voltage here is Vx, then what is the DC voltage you will get here? That is V1, because this is a full converter now. Of course, the firing angle is greater than 90, so it will work as inverter. So then what is V1 equation? If you recall, then you will get the same equation here: 3 root 2 by pi, 3 root 2 by pi. Okay, Vx cos alpha. So this is the formula you will get. This is the formula you will get. Okay. This we have already studied for the full converter. Okay. For the full converter. Now we will do one thing. We'll go ahead with this further. How to go ahead? You see this now. That is equal. We know very well this line voltage is VL, because the bus bar line voltage is VL. So the transformer other side line voltage is VL. The transformer, for example, you take this as primary. This you could take it as primary, this you take it as secondary, just for example. So the primary side voltage is Vx, the secondary side voltage is VL. So then assume that the ratio between VL and Vx, I hope you believe this thing, that this transformer secondary is VL because this is directly connected to the bus bar. So the bus bar voltage is VL. So the same voltage is we are giving to the stator. So VL is here, Vx is here. So we will take an assumption that the ratio between VL by Vx is equal to AT. What is AT? Is the turns ratio of the transformer. Here, what is a turns ratio of the induction motor between stator and rotor? Here, AT is turns ratio between the secondary and primary. So VL by Vx. So I will take VL by Vx as AT. Okay, because one A is there already. So to differentiate this, I will take it as AT. So turns ratio of the transformer, AT. Then if I take this one, then what is Vx from this? Vx is equal to VL by AT. Okay, so what is the purpose of doing all these things here is that, what is the purpose doing is that we want to convert everything into VL so that the remaining variables will remain there. So when we do this, what is the answer we will get here is that 3 root 2 by pi, what you will get here, Vx I will get VL by AT into cos alpha. So 3 root 2 by pi VL by AT cos alpha. This is the formula for V1. So we got the formula for now V1. We got the formula for now for V1, and also for VDC we got the formula. Okay. For VD1 and V1 we got the formula. Then what's next is now we will see the observation here now. What is the observation we will find out here is that if you look at the circuit diagram, let me go to the circuit diagram. We will apply KVL here. I want to apply KVL here. We will apply KVL here. So if you apply KVL here, now we know very well this thing that, see, when you give alpha greater than 90, when we give alpha greater than 90, please see this. If alpha greater than 90, it falls into second quadrant. If it falls into second quadrant, what is the cos alpha? Cos alpha becomes negative. So if cos alpha becomes negative, then you will find out here plus, here minus. You will find out. Whereas this DC, you know very well, this is plus, this is minus. I'm just finding out the polarity here. This is minus, this is plus. You must get like this. Then only, because alpha greater than 90, so cos alpha is negative. So definitely this V1 will be negative. So V1 will be negative in the sense, what does that mean? This is negative, this is plus. This is negative, this is positive. Whereas the output of the rectifier, this is plus, this is minus. Then I will apply KVL in this. If I apply KVL in this, then this VD1 plus the voltage drop across your inductor plus V1. So sum of all these three voltages will be 0. But one thing is that as the current you are maintaining constant in the inductor, then if you maintain the current constant in the inductor, the voltage drop across the inductor is 0. So I will write here VD1 plus VL plus V1 is equal to 0 as per if you apply KVL here. But you know VL is equal to 0. Why? Since ID is constant. ID is constant. Okay. So then what is left now? VD1 plus V1 is equal to 0. So we got this equation. From this we will substitute that 3 root 2 by pi into SVL by A. Okay. SVL by A plus 3 root 2 by pi VL by AT into cos alpha is equal to 0. Then few things will get cancelled here. 3 root 2 by pi VL. So I will write here S by A plus cos alpha by AT is equal to 0. So from this, what I can write here is that from this, I will write this thing S is equal minus A by AT into cos alpha. Okay. For example, if I take only the magnitude, say for example, then because slip is negative in the sense you got some other answers, and also cos alpha is greater than 90. So we will take magnitude here. So if I take only magnitude, you will get A by AT. So this is the relationship we will get here. What is S here? S is the slip. What is alpha? Alpha is the firing angle to the inverter bridge. Alpha is the firing angle to the inverter bridge. S is the slip here. Whereas A is the turns ratio between stator and rotor of the induction motor. AT is the turns ratio between for the of the transformer. AT is the turns ratio of the transformer. Okay, this we got here. Once we got this, now we will use this somewhere else. We will use this equation somewhere else. So before you use this further, we'll do one more thing. Okay, so we'll do one more thing. What we will do here is that, so what about the air gap power here? If we take the system ideal total, if we take the system total ideal, then if I take the system ideal here, what is the air gap power here? SAG. SAG is the air gap power. So which you are collecting from this side, which you are collecting from this side, and we will take this entire parts are ideal elements. So then I can say this thing that this power SAG is nothing but the power here. The power SAG is the power here, because the all the elements present between this point and this point are ideal we are taking. So if I take ideal here, then all these elements there is no power dissipation. Then whatever the power here will be same as this power. So I will write this thing here. What I will write this thing here is that, yes, the slip power is equal. What is the power at this point? The power at this point is the voltage into current. What is the voltage V1? What is the current ID? So V1 ID. V1 ID. Then from this, from this we can simplify. But before we simplify, we recall the equation between the torque. What is the equation between the torque and the air gap power? So this also we know that is also comes from the previous induction motor classes, that I will write here. T into omega S. This is the relationship between torque and air gap power. What is the relationship between torque and gross mechanical power? The relationship between torque and gross mechanical power is that gross mechanical power is equal to T into omega R. Whereas the relationship between air gap power and the torque is air gap power is equal to torque into omega S, not the omega R. So this already we studied. So you recall that. Then we substitute here. If you substitute here, what is the thing you will get? S into T into omega S is equal to V1 ID. Then, so from this we can find out what is torque. Torque is equal to V1. What is V1 equation we got? Somewhere we got the V1 equation. This equation is there. So we will write this equation. Three root 2 by 5 VL by 80. Into cos alpha ID into ID into ID divided by S into omega S. So now here we'll do one thing. What is S here? We got an equation for S here, this side. A by AT. So we'll substitute this equation here in place of S. Then A by AT. So AT will get cancelled. So then you will get A here, and cos alpha will get cancelled. So we will write here 3 root 2 by 5 VL into ID by A omega S. Just we will cross check once again here. A by AT cos alpha. So AT will get cancelled. So cos alpha will get cancelled. So these two will get cancelled. Then what is left here? A is left here. Okay. So this is the relationship between torque and speed. You see the speed here. You see the torque here. Speed here, torque here. So then we will draw the relationship between speed and torque. Of course, one thing I will tell you. One more thing is that. We'll put here, once again we'll put here, yep, omega S we can write it as omega R into 1 minus S. I hope you know this thing. Okay. So is this correct? I don't think so. It is not this relationship. So there is a relationship between. Okay, I will write the relationship here. Better I will use this equation, omega s minus omega r by omega s. Okay, then omega r is equal to omega s into 1 minus s. That's it. Okay, so this is the relationship we got. So from this we can find out what omega s we can convert it into omega r. So that is the rotor speed. So we will get the so once again you will get the slip here. So that slip is a function of cos alpha here. So it is up to us. Then what is the one thing you can say this thing that the the torque and your speed are inversely related. So then if they are inversely related, I will take this as torque, I will take this as speed. Then you will get these graphs. I will draw the graphs here. Different graphs I will draw, and these graphs are for different values of alpha. This is alpha is equal to 90, alpha is equal to 100, alpha is equal to 120. So you increase the alpha value, so the graph will come down like this. Okay, this you can find out by substituting s here. So first you substitute omega s here. So omega s is equal to omega r by 1 minus s. So your 1 minus s will go in the numerator. Then s place you substitute a by 80 cos alpha. Now you go on change the value of alpha, you will get this graph. But one thing is that both are inversely related, so you get this graph, and this is about this. Okay. So now one thing I will tell you now. I will draw another graph, another. I will draw another circuit diagram for the same static Scherbius drive, but only one change I will do. That instead of having the rectifier here, instead of having the uncontrolled rectifier here, we will have controlled rectifier. So, so I will just read down. So rather than reading down, I will just copy this entire picture. Yeah, please, just I will tell you the difference here. The only difference I will tell you here. Everything is same except instead of having the diodes, you have the thyristors. So I will just highlight this here in the picture so that I don't need to redraw the picture here once again. This is another type of Scherbius drive. See, both does the same function. The explanation which I have given will remain same, except now the equations may vary here. Why it is? The equations now here for VD1 also you will have the equation in terms of cos alpha, because this alpha is different, this alpha is different. So I will take it as alpha 1, I will take this as alpha 2. So this is the only difference. So we will use this when we will use this and when we will use the previous circuit diagram. So this is also static Scherbius drive. Okay, so this is also called static Scherbius drive. So previous one is also called static Scherbius drive. The difference between the previous picture and this picture is that in the previous picture, the rectifier is the uncontrolled rectifier. Now it is a controlled rectifier, and there is no other difference. So with this difference, of course, the equation also a slight variation will be there in the equations also. Okay, but the same analysis you can do here also. But I will tell you when we will use this one and the previous one. So what is the advantage of this one is that the advantage here is that you can run the induction motor now here at both sub-synchronous speed and super synchronous speed. Okay, I hope you know what does this mean. What is meant by sub-synchronous speed? Sub-synchronous speed in the sense your NR value is always less than NS. Okay, this is sub-synchronous speed. What is super synchronous speed? NR is greater than NS. I hope you know these words, sub-synchronous speed and super synchronous speed. So the first picture, it is only for sub-synchronous speed. Okay, so how do you do this thing that sub-synchronous speed and super synchronous speed here is that sub-synchronous speed in the sense NR is less than NS. So if NR is less than NS, so the slip is always S less than 1. So the slip is always in between 0 and 1. Okay, if NR is always less than NS, definitely the slip is between 0 and 1. So if the slip is between 0 and 1, it means you are operating your induction motor in induction machine in motoring mode. So that is this slip. So this circuit diagram you will use only for motoring condition of your induction machine. That is the slip is between 0 and 1. Okay, when you have the uncontrolled rectifier. Whereas whereas when you have this controlled rectifier, you can use even this for NR greater than NS also. That is for super synchronous speed also you can use this. Okay, but one thing I will tell you that a super synchronous speed, in the sense, what does this mean? That your S is okay, I will tell here, regenerative braking. In case of regenerative braking also you can use. So what is the regenerative braking here is that S less than 0, you recall this thing. So if S less than 0, you recall S is equal to NS minus NR by NS. Okay, so when you have this, how can you make this slip negative? To make this slip negative, okay, to make this slip negative, you can do one thing, that you can reverse the phase sequence here. Reversing the phase sequence, you reverse the phase sequence here. So if you reverse the phase sequence here, if you reverse the phase sequence here, what will happen? NS becomes negative. NS is now negative. If NS is negative, then this is negative, this is negative. Okay, so of course, okay, sorry, I think this is not possible. So if you do this thing, if you do, okay, if you do this thing, what will happen now? NR always try to follow, NR always try to follow the synchronous speed. So if it is following the synchronous speed, then what do you find out is that, okay, so it slows down. If it slows down, you call that as the regenerative braking. So I think in the braking condition it is s greater than 1. I'm sorry, I think it is s greater than 1. At s less than 0, s greater than 1. Okay, so this is the condition you will find out. So you can run either for super synchronous speed, but remember now, super synchronous speed in this, this is the actual condition, NR greater than NS. Now you see yourself, if NR greater than NS, what it becomes? S less than 0 it becomes. Okay, in another words, for example, you reverse this NS, if you reverse this phase sequence, then it becomes minus NS. So minus NS minus NR by minus NS, everything is minus. Once again, the slip is positive, but in this case S is greater than 1. So any operation you can make here using this picture. How you can make this picture is that you control the firing angle of this one. Either you for example, I will tell you that this is acting as inverter, or this is acting as rectifier. So you change the roles of this. See, controlled you have two controlled rectifiers here. Okay, you have two controlled rectifiers. I told you already that full converter can be work as either a rectifier or the inverter, depends upon the value of alpha. Here also same thing, either it can work as a rectifier or inverter. So one thing, you if you operate as rectifier, the other thing will work as inverter. You can reverse the role of this by changing the value of alpha. Here you put the alpha greater than 90, here you put the alpha less than 90. So it's something like a dual converter operation. You recall the dual converter operation. Okay, so combinedly you can call this as super. So you can run this at super synchronous speed, whereas the previous one you can run only at the sub synchronous speed. So but remember now, both the cases it is Scherbius drive only. So both the cases you are recovering the seat power. Okay, now the same thing you can recover. You have another circuit also other than these converters. Which converters other than this? Other than this full converters, we will use cyclo converters, because you remember. So you remember now what a cycloconverter does. Okay. So then you have the rotor. The rotor terminals are there. Three terminals of the rotor. So each terminal, one cycloconverter. Now the output of the cycloconverter is coupled to the bus bar. So So why you need a cycloconverter is that you should match the frequency of the bus bar. The bus bar frequency you should match with this. So what you do here is that you will use the full cycloconverter here, full wave cycloconverter here. Then by triggering the firing angles here, the rotor frequency is there. The rotor frequency. The rotor frequency you will match here using this also. Okay. So this is another type of converter which you will use for the flip power recovery. So as of now, you see here these three we have studied. So Scherbius drive for subsynchronous speed, Scherbius drive for super synchronous speed. Then using the cycloconverter also, we can just do the same thing. Okay. So now what else is here? So I will just briefly summarize this here. What is Scherbius drive does is that the Scherbius drive, so it simply the Scherbius drive, it recovers the sleep power and it will feed to the bus bar. This is what it does. Now conventional system, you don't find out any kind of you find out all these motors and machines and so on and so. Whereas the static Scherbius drive, you find out the power electronic converters. Once again, you have two bridges here, diode bridge here, thyristor bridge here. So that case you will use for subsynchronous speed. Whereas if you have both the bridges, controlled bridges, then that you will use for super synchronous speed. Okay. Now we will draw the closed loop diagram. We'll draw the closed loop diagram. So see the closed loop diagrams, many of the closed loop diagrams are very same. Okay. Same controllers you will find out. Same feedback is there. Everything same you will find out. Okay. So, but anyhow, still we need to discuss briefly. Not in detail, at least briefly we can discuss because all the things which we have studied already, it is there. So stator, same thing. So then rotor, what you do here? So rotor connection. So rotor connection goes to, we will just recall this subsynchronous speed because many times you operate the machine in the motoring mode only. So that case we will take. So this is a diode bridge. Okay. Then after diode bridge, this is block diagram I'm drawing. So this is LD. The current here is ID. Okay. Then after that we have a thyristor bridge. This is thyristor bridge. Then the output of this thyristor bridge, okay, is going to transformer. Is going to transformer. Okay. Okay, then now we will go to the feedback part. So feedback path is means first of all we need to give the firing angle here. Just remember now, feedback in the sense the base circuit. So we have to give the firing angle here. So then we will sense the speed here. All these are very common. This is a speed sensor. So this speed sensor, the actual speed will be compared with the reference speed. This is the reference speed. So plus minus, then you have some error. Then that error will go to the speed controller. Then it will go to the current limiter. I will write here. Then it generates the reference ID. This ID is there. So this is the reference ID it generates. Then this reference ID should be compared with the actual ID. So you tap a current here, ID, the ID which is flowing here. You sense ID here. So this is plus, whereas this is minus. Then once again you may have some error. Then that error goes to the current controller. Then based upon the command from the controller, you have this firing circuit for the thyristor. So that goes here. That's it. This is the closed path. This is the closed loop control of static Scherbius drive. So this part is the power circuit. We can call like this. This part is the power circuit. This part is the control. We can call it as feedback path. This is forward path. We can, no problem. You can divide into any way, no problem. It may not be the same. But remember, this one is the power circuit, whereas this is the control circuit. So what you require for the power circuit, based upon that only you design the controller. First of all, what you require, what you want to do. First of all, you want to set a reference. You want to run the induction motor at a particular speed. So how do you run that? Then definitely you will take the feedback of the speed, because you want to run at a particular speed. So that speed is reference speed. So this reference speed will be compared with the actual speed of the induction motor. Then you got some error. Then that goes to the speed controller. Then that goes to the current limiter. Then this current limiter will tell what is the reference value of the current here. Which current here? This current here. This inductor current. So then actual inductor current we will compare. If there is error, then that goes to the current controller. Then after that it goes to the firing circuit. So you need a firing circuit here for your thyristors, because you have the thyristors here. So that firing circuits input you are getting from the current controller. So this is the closed path.